Good morning, everybody, and welcome to our workshop dedicated to district heating and cooling networks. My name is María Victoria, and I'm working at the engineering department of ACCIONA in Spain, and I will guide this interactive workshop. I would like that all speakers turn on the camera just to see our faces, just for a second, if that's possible. I'm going to give your little bit more space to see your faces. Hello, everybody. So the objective of today is that, well, we would like to share with you some experiences and lessons learned that we are facing in our European projects when we want to implement some district heating and cooling projects. We have different projects, so the idea is to share all our knowledge, and well, any feedback is welcome. So we have 2-hour journey together this morning, so I hope that the workshop you enjoy the workshop and everybody's happy with the results and the conclusions of our workshop. Then I'm going to share my screen. Then thank you, all the speakers. We will have the opportunity to listen to you. You can turn off your camera because I'm going to share the screen. Then let me show you. Okay. Hopefully you will see my screen. If not, please inform me. So for the audience, you can write in the chat. The chat is open, and you can write whatever you want. You can write ideas. You can write your feedback. You can write doubts or questions. We will be happy to answering you and also interacting you, because this is a workshop. So this is open for everybody. Then let me move. Okay, so this is the agenda for today. I will start with a very short overview of the WEDISTRICT project, and then we will follow with a set of the different presentations with, as said before, with our different experiences and projects and lessons learned, which is the purpose of the workshop. The idea is that all speakers should last around 10-12 minutes of presentation, and then there are some minutes for answering your questions if there are. So please don't be shy and feel free to ask to our speakers. Okay. And since I want that this session is interactive for everybody, first thing what we are going to do is to interact with you. So please go to www.menti.com and introduce the code 44479401 in order to answer two questions. So the first question is just to know where you are, so which is your professional sector, and the second one is just what do you think about which are the main barriers or limitations what we are aiming to implement a new district heating and cooling project. Is something that you can have an idea, or maybe something that you can imagine. So don't worry, because this is anonymous. Then what I'm going to do is to share the screen, because we will be able to see the answers all together. So I hope that we can see all together the answers in a moment. So please go to menti.com. Let me, okay. It's a bit slow, but it will work. Okay, people is answering, right? This is the first question, then we will move to the second question. Okay, great. So please go to menti.com and introduce the code 44479401. It's perfect. Okay, thank you very much. So many people from scientific community and also consultancy, right? Okay, so then let's move on to the second one. Second one is you can write your opinion about which are the main barriers and limitations. So as said, this is anonymous, so don't worry if you say something that maybe is not true, but it's just to know what do you think, okay? Maybe you have some experiences, so that could be great. But if not, what do you think? Regulations? Regulations is something that, yeah, it seems, no? That could be a limitation or a big barrier. Permits and licensing, high cost. Yeah, yeah. It's the costs. Yeah, financial aspects, economics and permits. It seems that we are all aligned. Payback, costs. Mhm. Access to renewable sources energy. This is quite interesting. Mhm. Licensing, brilliant. Yeah, yeah. I think that we are all aligned. Okay. Thank you very much for your answers. Because, well, maybe after the presentation, maybe we have another idea or we confirm what you were thinking. Then, let's, as promised, just a couple of minutes about what is the WEDISTRICT project. The WEDISTRICT project is a funded project, European funded project, deals with the development of different district heating and cooling solutions, fossil-free, so renewable solutions that can be implemented in district heating and cooling networks. Well, considering that almost 70% of the energy generated comes from fossil fuels, it seems a good idea to think about renewable sources for this kind of projects. So it's what we aim under the WEDISTRICT project. These are all our technologies. There are 3 different solar technologies that are under development. A new enhanced low emissions biomass technology, a hybridization of thermal and electrical systems based on photovoltaic and geothermal energy, 2 different cooling solutions for district heating that can be fed by renewable energy sources. One is based on absorption chiller and another one is a renewable air cooling unit. And a new innovative waste heat recovery from data center that will be presented after in one of the presentations. Very interesting and very pretty, I'm very sure. And another new innovative energy storage molten salts based instead of water, which is also an well, innovation for the district heating and cooling sector. And of course, we need to well, make operate all together in the most optimal way. So we are also developing an advanced digitalization system for succeeding. So all our technologies are being developed, but will be also deployed and demonstrated in real cases. 3 of them are going to be presented today in Alcalá, Luleå, and also Bucharest. There is another one is in Poland. In Poland, what we're going to do is to replace the coal boiler, the coal and dirty boiler, with a biomass boiler and also photovoltaic system in order to feed the electric purposes. And besides our real cases, we are also working a lot with virtual demosites. 11 virtual demosites joined to the project, were very interested in our project, and we are studying different scenarios and different locations and different use cases for assessing the replicability of the WEDISTRICT solutions in order to finalize with a catalog of different solutions for district heating and cooling networks. These are our main numbers. The funding, this is a quite large consortium, 22 partners from 9 countries. And here is our family, our partners. And last but not least, you can visit us in our social media and also follow us in Twitter and LinkedIn. Also, you can visit our webpage. There is a lot of information. It's really updated information. You can also subscribe to our community of interest. And if you're curious, you can know more about the WEDISTRICT project. So that's all from my side. So then we could start with our sessions or different presentations from our speakers. So I would like to let John Martinez to start with the Alcalá demosite from Redistrict project. John Martinez from DH Eco. So John, you can turn on your camera and start sharing your screen. Hi John, we can see you.
Thank you. Hi, Mavi.
Hi.
Thank you. Okay, I will try to share my screen.
Mm-hmm.
Okay. Can you see it?
Yes, George.
Yes, we can
yes,
see
yes.
Is it okay?
Yes, George.
Okay.
You can start.
Okay. Okay. Thank you. Good morning, everyone. My name is John Martinez, engineer at DHC Energías. It's a partner of WEDISTRICT project and responsible of Alcalá demosite. The new district heating and cooling in Alcalá de Henares will be deployed. Alcalá is a 200,000 inhabitants city in Spain. On the outskirts of this city, near the new campus of Alcalá University, there is a technology park where the district heating and cooling will be built. The new district heating and cooling will supply energy to only one building, which is the R&D center of the company's CEPSA. It has a yearly heating demand of about 1,300 megawatts hour and a cooling demand of 730 megawatts hour. The current energy sources are gas and electricity. They supply the energy with natural gas boilers and chillers. The district heating and cooling will integrate three different technologies of solar thermal energy that you can see here in the green, blue, and purple areas. And the pink color area is where the new power plant will be built and will be located. This is the shape the new building will have. It stands on one floor, occupies approx 600 square meters, and the maximum height is 12 meters. I'm going to briefly explain the hydraulic scheme of the power plant. On the primary side, there are two circuits installed in parallel to heat the water. Here you can see the low emission biomass boiler, and the other circuit goes to the hot water tank that stores the energy, the produced energy by the three solar thermal technologies, the 1, 2, 3 points. On the secondary side, there are three circuits. One is the district heating network, this one, the third one, that connects the CEPSA building, and the other two circuits feed the cooling technologies. There are two chillers in the power plant. The one is the high efficiency absorption chiller, and the other one is a commercial chiller. The chilled water circuits from both chillers merge into one cold water circuit that is the district cooling. This one that connects to the CEPSA building. Soltigua, explaining the solar installation here. Soltigua is an Italian partner of WEDISTRICT project and provides two solar technologies, the parabolic through collector and the linear Fresnel collector. The PTC consists of parabolic through-shaped mirrors that concentrate the solar radiation along a heat receiver tube. The PTC plant has a peak capacity of 186 kilowatts. The Fresnel collectors consist of multiple, is this second image, of multiple lines of mirrors that concentrate the solar radiation along a heat receiver tube. The total installed power is almost 250 kilowatts. Censo, another partner, a Spanish partner in WEDISTRICT project, will install the tracking concentrator for fixed steel collectors, which are composed of 2 lines of 20 panels each. The total installed power of this technology is 242 kilowatts. Inside the power plant, we will install a biomass boiler provided by CERN with a nominal power close to 1 megawatt. American Air Filter, and another partner within the project, is in charge of the purification of the exhaust air that comes from the biomass boiler. A catalytic and non-catalytic filtering systems will be installed, and these systems are composed by a multicyclone, a catalytic reactor, and a series of bag filters. Talking about the cooling production to meet the cooling demand of CEPSA building, there are 2 absorption chillers, as explained before. The first one is the high efficiency absorption chiller, that is a prototype model created by University Rovira i Virgili with advanced features and improved performance. It has a cold thermal power of 100 kilowatts. There is also a commercial chiller that is a conventional model of cold thermal power of more than 700 kilowatts. It is a single effect absorption chiller by the brand Hitachi. There is also a third cooling technology that is the renewable air cooling unit, the RACU. It is a desiccant indirect evaporative renewable cooling unit, mainly composed of an indirect evaporative cooler and a desiccant wheel that can independently control the air temperature and humidity. So this RACU is fed by the district heating. It is not located in the power plant, but in CEPSA building, and it will air condition a room, 50 square meters office room in this building in CEPSA. Regarding the control of the power plant, the monitoring system and the outputs of the prediction services allow Atos partners to manage and control the district heating and cooling, forecasting the solar energy generation and also the energy demand in CEPSA. The command and control suite is the central module in charge of the automatic control and optimization, and technically it can be split in 4 individual elements: the general control system, the system optimization, the command and control dashboard, and a smartphone app. I think there are 2 main lessons in these first 2 years of the project. At the beginning, the idea we have, and that's the way we wrote the proposal, was to split the heating production into 2 parts, one with high temperature solar installation, which was connected to a thermal energy storage composed by molten salts. We made the engineering part, and we saw that the budget of this specific installation was much higher than was expected. It raises the budget by almost 100%. So it was out of our budget. We had their limitation of economic limitation, but also we knew. We didn't know before when we wrote the proposal, but we knew later with talking with experts in this field that this kind of installation, there are a problem in the startup stage, which in this case could complicate the validation of the technology due to the time constraints that we have in the project. So, as a lesson learned here, I think we can say that that due to this complexity, or the complexity that this installation has, we think that is economically and technically feasible for a bigger sized project than this one in Alcalá. The second lesson is one of the biggest problem in this kind of projects, that is to avoid as much as possible the uncertainties with municipal licenses. We are finding some problems to get them, although we are in a good line. But when we prepared the tender, we did it along with the Alcalá City Council. We talked with them. They gave us a support letter. So we thought everything was on the safe side. But then always there are changes. In this case, the City Council, the technical staff of the council changes. So what we thought that was sure, finally it's not, and we had to fight again to obtain these municipal licenses. So as a lesson learned, I think that it would be a good move for future projects to include the City Council as a consortium partner since the beginning, to involve it as the rest of the consortium partners. Okay, thank you. For my side is all. Thank you very much for your attention. If you have any question, I'm pleased to answer them.
Mm-hmm. Thank you, John. Yeah, I don't know if someone would like to ask something about the Alcalá site. It's true that what you have said at the end is the licenses and permissions is one of the things that has been repeated in the questionnaire launched before. But yes, it seems that it's something common that, and I don't know how, well, in fact, we cannot change this. It's not on our hand. But well, hopefully this will improve in the future.
Yeah, we have talked a lot about this problem, because if you ask before in the tender process for the municipal licenses, they have a due date and you have to build the project in 6 months on a 1 year period. So we wouldn't be in that mood, because there are some more or less 1-2 years before from the beginning of the project until we start the works, the construction works. There are some months, and it's not possible to ask from the Commission, the European Commission, to ask for these municipal licenses to have them, because there could be a time problem. So it's like a difficult balance from the European Commission, and also for us, for the consortium partners, to get them when we want.
There is a question, John. You don't see the chat. Okay. How about the temperature level of your solar thermal units? Are there issues in combining them to the fossil generation?
No. There are not, because we thought to go to up to 250 degrees when we thought in this thermal energy storage by molten salts. But now, as we have changed the hydraulic scheme and everything goes with water, we think that we can store the water at 100 degrees. So we are at low temperatures, and these solar technologies are perfect for them. So the district heating supplies water at a maximum of 95 degrees. That is what it meets the needs of CEPSA building.
Yeah, there's another technical question very quickly. What is the COP, the COP of the advanced absorption chiller at nominal conditions?
Nominal conditions. I don't know. No, I'm not sure.
If I remember, let me answer you. If I remember well, the COP is a single stage absorption chiller. It's enhanced with a double heat recovery system, and improves the COP and if I'm not wrong, should achieve around 1.2, 1.3. Which is quite good compared to the conventional single stage absorption chiller, which is around 0.6, 0.7. And last question, okay, this is well, it's a comment. This is a real difficulty: how to address innovative projects in the current public market tenders framework. Yeah.
How to address the
innovative projects in the
innovative
current public,
projects in
the
current
current
public.
public market tenders framework.
Yeah, it's difficult, but in our experience, the way to work is to try to go for these innovative projects, see if there are some technologies that you can use in tenders or in commercial projects, as we do in DH Economías do in Spain. So when we think that one technology is able to go for commercial projects, we bring it and put it in other tenders or other projects. So we have to see our first idea was, for example, to use the molten salt storage in more than one project. But now, for example, we have seen that there are some problems that we may stop this installation in our commercial project. So we have to check when the technologies are enough mature to bring them.
Yeah, well, in fact, not all our WEDISTRICT technologies are at the same TRL level, that is maturity level. So the case of the molten salt is at lower level, but there are other technologies that start from a higher maturity and could be possible to place it on the market after the project. Well, and there is a comment. It's also the issue of who bears the risk for new technologies in such constrained contexts, which are barriers to innovation. Yeah. Yes, Modest. Okay. So thank you, John. Thank you, John,
Okay.
for your participation. And we can follow with the presentation of the Bucharest demo site. Also comes from WEDISTRICT project. And Constantin Ionescu from University Polytechnic of Bucharest can share the screen.
Yes, just a second.
Okay, Christy is here. Hi, Christy, good morning.
Can you see my screen?
Okay, we can see your screen. Perfect.
Okay, perfect. Hello, everybody. My name is Constantin Ionescu, and I'm responsible of project partner University Polytechnic of Bucharest. Also, UPB is responsible for the development and implementation of Bucharest demo. Before presenting the demo, please let me say a few words about the location of the Bucharest demo site. Here you have a map of the University Polytechnic of Bucharest campus, where our demo installation will be implemented. To demonstrate the functionality of the proposed demo, we have chosen a target building. And this building is, in fact, a laboratory of our faculty of Energy Engineering. The heating demand of the entire campus is currently assured by a cogeneration plant based on natural gas, so no renewable energy sources involved before WEDISTRICT. And currently the target building is not supplied with heat from the local district heating being assured locally by electrical heaters. Through WEDISTRICT project, the building will be reintegrated into the university heat distribution network. The main objective of our demo is to generate three forms of energy: electricity, heat, and cold, based on a mix of renewable energies, geothermal and solar. Geothermal, here we are speaking about the ground the energy of the ground, not the geothermal, as most of the people knows, the hot water that comes from the ground. So is the heat stored in the ground. The electricity produced by our demo, our electrical part of the demo will cover at least the consumption of the thermal energy production unit, considering this in a yearly basis. The heat produced will cover the demand of the building, and our production of heat will be injected in the local district heating network through a new pipeline. In order to ease the process of replication and scaling, the development of the demo was made considering a modular concept. In this sense, the Bucharest demo is composed of two subsystems, the thermal one and the electrical one. Briefly, the thermal subsystem is the section of the demo used to generate heat and cold, and the electrical one is the section that will generate the electricity to cover the consumption of the thermal part in a yearly basis, as I mentioned before. The electrical section of demo is based on a photovoltaic plant. Therefore, we can consider that at the level demo site, we will have zero CO2 emissions. In the next slides, I will present you briefly the two subsystems. Here we have the final layout of the thermal subsystem. It is based on two heat pumps with a total heating power of around 63 kilowatts and cooling power of 50 kilowatts. They are working in a master-slave configuration. The heat pumps are of groundwater type, and they are using the energy extracted from the ground by the means of borehole heat exchanger composed of 12 geothermal probes. During the heating period of time, the heat produced by the means of heat pumps is stored in a 2,000-liter storage tank. And from here, by means of a distributor, the heat produced is distributed to the heating system of the building, to the domestic hot water preparation tank, and to the heat exchanger for injection in local district heating. During the summer, in the first part of the period, of the cooling period, the cooling is assured by a passive cooling system, in which the ground heat exchanger only is used for cooling. During summer, the 2,000-liter tank is used for cold water storage. And from here, the cold water is distributed to the building to cool the building. When the cooling demand will increase, when we are moving to the middle of the summer, the heat pumps will produce cold water in an active cooling way. During the summer, domestic hot water is produced by a PVT panel, hybrid PVT panel system. The electrical subsystem consists of two low voltage subsystems acting as microgrids that will be installed in two different buildings. In order to have a realistic simulation of renewable energy sources implementation into a district, we have three different technologies. Here we are talking about three types of inverters from three different vendors, three types of batteries working on different DC voltage, and three types of PV panels from three different vendors. This setup will allow the study of multiple scenarios, considering the district as being an intelligent energy community with aspects of resilience, as the heat pumps can be supplied even in off-grid mode based on the battery installed in our system. One important section of our demo will be the system control and automation. There is a central equipment, the main PLC, which collects all data from the thermal subsystem equipment. The PLC equipment is also responsible for receiving set points from the SCADA EMS system developed in-house and to send to the subsidiary control equipment these set points. The overall concept allows integration of the thermal system in the overall SCADA EMS system of the WEDISTRICT project and to communicate on different levels, locally and remotely. Here we have an eagle-eye view of the deployment areas for the equipment. As I mentioned before, we have two PV arrays on two different buildings. The main building is the target building, in whose basement will be the technical room of the demo, where the heat pumps, storage tanks will be located, as well as the first bank of batteries for the PV array from here. The second PV array and the related storage system will be installed in this second building, adjacent to the target building. Close to the target building is the area destined to the installation of the borehole heat exchanger or ground heat exchanger. The first step of the installation phase, namely the installation of ground heat exchanger, is completed now. And here we can see in images the main steps of installation. First picture is a 3D drawing we made to have a better view of the ground heat exchanger. Next is the actual view of the borehole heat exchanger location, framed in red here, before installation starts. And the next pictures show different stages of the installation. The insertion of geothermal probes in the borehole, the trenches for piping circuits, and the connection of all 12 circuits in the main collector distributor. Regarding the thermal subsystem, the next phase is the installation of the heat pump system and the connection with the local district heating network. And that works will start next week. In parallel, we'll start the installation of PV and storage batteries. For the next month, our activities will be concentrated on finalizing all installation works and the commissioning, so that the demo will be up and running from the beginning of the next year. That is because, according to the project work plan, the functionality of the demo must cover at least 1 full year of demonstration. Considering the various working regimes of our demo, we have realized this a detailed operation plan. And this is based on climatic conditions for Bucharest that influence the heating and cooling period. If all will go as we planned, the entire year 2022 will be dedicated to demonstration. During the 2 years of the project progress, we have faced a lot of challenges, and we have a lot of lessons learned from that. The most important ones are summarized in these slides. We grouped the lesson learning in 3 categories. On technical categories, we can say that UPB team is based 100% on academic staff and PhD students. For us, the collaboration with experts from industry was very, very valuable in terms of sharing ideas, new concepts, new products on the market. The combination of our theoretical knowledge with their practical knowledge had a positive impact on the development of the demo. Another important lesson learned is that by using dedicated software to validate the solution could lead to to the reduction, important reduction, in fact, of time invested in development of demo. Also, double checking of the results by using multiple calculation methodologies could increase also the quality of results. On the financial aspects, consideration of allocation of a higher budget margin for a specific equipment material or any category at the time of the project proposal writing will amortize the possible price rises during the project development. This is what happens to us this year in the beginning of the year when we start to purchase the materials, and all prices comparing with last year increased a lot. Also, another important aspect it was that for countries as Romania that have no euro as a national currency, the exchange rate should be considered. In particular case of Romania, the fluctuation of exchange rate has a negative impact on the budget, since the national currency is continuously depreciating. As an example, because of the depreciation of the Romanian currency in the 2 years of the project, we are losing now 4% for each currency exchange. That means for each 100,000 euro, we have losing 4,000 euro just from exchange rate. And in our case, 98% of the budget should be converted from euro in national currency in order to pay the salaries, equipment, materials, and all other expenses. Also, the acquisition contracts should be clear, detailed, and the special attention should be paid to the execution time, guarantees, and also to the penalties. Another important aspect that should be considered in the allocation of time is allocation of time and the human resources. Our experience in the last months show us that the obtaining of the permits and licenses are a time-consuming activity. And the time we have allocated was underestimated. And I saw in the presentation of John, they had the same problem. This is, in our opinion, mainly because of sometimes very complicated bureaucratic process and also the lack of communication between entities involved in this process. Also, the public tenders are high time and human resources consumers. Here is important to always consider a buffer of time in case that after the tender evaluation, one of the tenders who lose will challenge the results of the procedures, and that will conduct to the delay in the acquisition process. Regarding the research team, it is very important to have persons with multidisciplinary abilities that will avoid the situation of getting stuck in a specific issue if the person involved cannot contribute for a certain reason. And of course, constant communication of team is the key to success. Here at UPB, because all team members are teaching staff, having the teaching duties and different schedule, it's difficult to find a day or hour when everyone can join a meeting. Consequently, we have formed small working groups, more flexible, each one with a responsible that is in permanent contact with the demo coordinator. That is briefly the presentation of our demo. Thank you for your attention. If you have questions, I would be happy to answer to them.
Thank you very much, Christy. Thank you. And very useful, your lessons learned. I have to say, from the Redistrict coordination, that these lessons learned from the UPV are really reference for us because they are working very well. And
Thank you very
well,
much.
it's yeah, I always say that they are a mirror for us because yeah, they are our reference. They work well. It's a pleasure work with the UPV team. And
Thank you.
just we are a little bit delayed, but I would like to add one remark about what you mentioned, the budget. Because it's true that, well, I think that is something that is happening right now, is that the raw materials are really, well, has increased a lot the price. And also the providers are extending the supplies
Yes.
because there is no raw materials. So it's a problem that
Yeah.
we are facing at this moment. It's not a problem of us in particular, but it's something general. And it's true that when we
Yeah.
wrote the proposal in the proposal phase, who could know what will happen in 3 or 4 years, no, after the so it's difficult to propose. There's a compromise about what is the
Yeah.
maximum funding that can request to the European Commission, and to be aligned with the reality in 3 years. But well, this is first year lesson learned, and something you have to consider for any proposal. So well, I think that we have to move on because we are a little bit delayed. Thank you very much, Christy.
Thank you
If
too.
there are any particular question from Christy, for sure, you have my contact. Also, you have your contact. You can put your next slide
Yes.
with your
Yes.
contact. Yes.
Excuse me. I forgot.
No worries. And yeah, we'll be happy
Yes, you have my
to chat
contact
with you.
here. Any questions?
Okay.
Is
Thank you. Thank you very much,
thank you.
Christy.
Thank you too.
Then we can continue with the next presentation. We'll present the Lulia demosites. John is here. Hi, John, from RISE. So
Mavi.
the floor is yours.
Thanks very much, Mavi. Let me just share the screen. Hopefully you can see the screen very shortly. Okay, good morning, everyone. Yeah, great. Yeah, I can see it as well. Yeah. So this is slightly different demo site to the other two that have been talked about because we already have an existing district heating network here. So it's about data center waste heat recovery with a slight difference. So we're, my name's John Summers. I'm a scientific lead in data centers at Research Institutes of Sweden. This particular unit, which is the ICE test and demo unit, is based in Luleå in the north of Sweden, very close to the Arctic Circle. And what we're doing is we're trying to combine the excess heat from the data center with fuel cells that are powering the data center in order to upgrade the heat to the level where we can actually supply it to the local district heating network here. So let me just go to the next slide. So the question really is why do we want to recover waste heat from data centers? And there's a lot of growth in data centers around the globe as digitalization takes on a new level. We're seeing a digitalization across the globe, even in third world countries now, where it's become very important, particularly emphasized by the pandemic that we've been going through at the moment. But what actually happens in a data center is it consumes a vast amount of electricity. And most of that, in fact, all of it really generates heat. And in most situations in a data center design is that this heat is actually vented to the environment or released in the environment and not used in any way. So there are calculations done, and I'd like to point out a very interesting paper that was written by an IBM researcher in 1961, actually 60 years, it was July 61, and that was irreversibility in heat generation in the computing process. So he showed that you could actually measure the energy value of the stream of digital information that comes out of the processing parts of the data center. And today, we are literally is 0.03% of the electrical energy that goes into a data center is actually measured in the stream. That says it's the energy value. It doesn't give you the value, the economic value, or any other value of the data that comes out of a data center, societal, whatever it is, frivolous activities that go on with social media, etc. So recovering the waste heat is a very important aspect. So that's the reason why we want to recover waste heat. So has it been done before? Yes, it's been done, in fact, in quite a large number of locations. So waste heat recovery is not a new idea. So I've listed here some waste heat recovery projects or some initiatives around Europe. So a lot of them are in the Nordics. You've got Finland here with the Andex data center. You've got the Facebook data center in Odense, Denmark. There is Gleesus in Sweden. There's even a project in France. There's one coming up in Ireland, I know, with the Amazon data center. There's also the Open District Heating network in Stockholm. And then there's the Telia data center, Fortrum Telian data center in Helsinki. Everything here, they have one common theme. In fact, they have two common themes. First is it's not just the data center. The energy provider is actually involved in the solution. The second common theme is that they all use a heat pump. So how do they recover the heat? Because the waste heat that comes from a data center, I've taken this picture here from the sustainability website of Facebook, and this is the concept that is being developed, if not even operational yet, in Odense in Finland, in Denmark, and that is that the heat is upgraded by heat pumps that the energy provider owns, and then the heat is then rejected into the district heating network and supplied to the urban community. So, but the question about heat pumps is that data centers, the data center community, as we know it, has been trying to use methods of cooling which do not use refrigeration. They're trying to get rid of refrigeration so that they do not have to deal with F-gas regulations, etc. And they can be seen to be more sustainable, but that means raising temperatures and possibly using more water in some situations. But who really wants to run a heat pump? Data center will not want to run a heat pump. So it really needs the energy provider to be invested in the data center design and build out. Because when you bring heat pumps into the mix, you're bringing the compressor back into the data center world. So it's something that they don't really want to do. However, fuel cells are something that data centers are interested in. And the reason why fuel cells are of interest is because there's quite a lot of gains that can be made in using fuel cells in the mix. First of all, there's the simplicity in the infrastructure. So you have 50% decrease in physical infrastructure that's required on site to deal with power. So this is the substation, the power distribution that's required at the data center. There's a lower cost of goods and services for the implementation of fuel cells. There's even an improved efficiency because you don't get there's less losses in the transmission. There's even greater improved efficiencies locally to the data center because it's actually fuel cells can produce direct current, for example, and all of the IT systems run on direct current, so you can actually leverage that aspect. And then the last thing is that, okay, fuel cells they're like a continuous flow battery. They require a fuel to continue. So it's same technology as in the electrochemistry of batteries, but it requires a continuous flow of fuel. And you could use a renewable natural gas for this, or in the future, as we might move to a hydrogen economy, you could run fuel cells on hydrogen. So you increase there's a lot of benefits in doing this, and this is why data centers are actually interested in using fuel cells. particularly as we start to get data centers in urban areas, as we need data centers close to the end user. So Amazon has made a pledge that it wants to provide sub 10 millisecond latency to everybody on the planet. And that means that you need infrastructure very close to the users. And when you bring it into urban areas, you put a stress on the power grid, but you also got the opportunity to use the heat, because people living in urban areas, they're very close by to the data center. Fuel cells are silent, are pretty quiet compared to other on-site generation possibilities. So yes, it has been done before, the use of fuel cells, but not in Europe. So this is something that has been happening in the US, and I guess it does have a little bit of political issues, because all the fuel cell infrastructure that's been built out in the US based on, for example, Bloom Energy, Equinix, for example, has installed it in 12 US data centers. Apple has installed 10 megawatts of fuel cells, and then in California it's being used, but it does use natural gas. So that is obviously a contentious issue, because it's not a source of renewable energy, is it? So, but the message is clear, is that if you are using fuel cells, you have the opportunity to combine the heat from the fuel cell with the heat from the data center in order to provide heat to a district heating network. So there are some advantages, and as we can move, if we can move to renewable sources of natural gases like biogas, etc., or mix in hydrogen into the mix and reduce the carbon intensity of the gas, then there are some opportunities there. So what we're going to do in the demo site in Luleå is to combine the excess heat from the data center, which we've decided to go for a liquid-cooled data center because we're using immersion technology. Again, this removes fans, so we have no fans in the actual data center part, which also reduces the noise levels as well. Using pumps are regarded to be quieter. And then, but the challenges we have with this is that Sweden is not the best place to do this. First of all, you have no piped gas, so we have to use gas that is stored locally, which is a challenge for us. And also, being in the north of Sweden, we are connecting to a third generation district heating network, which is a high temperature network. So it obviously challenges us further, because we need the higher temperatures from the solution. So it's going to be a small data center. So it's the kind of size of data center that you would see in urban areas for what's called edge of network infrastructure, so close to the end users. So this is a plan of our facility. This is a cold storage facility where we have our research labs. We're going to put the data center and the fuel cells in 2 containers stacked on top of each other in the car park here. And then we are going to put some biogas, 4 tons of biogas, locally stored at around about 15 meters away from the building for safety reasons. This will be stored at 200 bar pressure, and we need a pressure reducing system which drops the pressure, so that, because the fuel cells consume the gas at about 20 millibars maximum pressure. And then we will have to pipe the gas to the data center and the fuel cells. We also have challenges sometimes with outside temperatures as low as -35 to deal with as well. So when you're dealing with certain fluids, you have to think about the issue of things freezing and causing problems in that situation. So that is also another challenge for us. So this is the biogas storage and the 2 stacked ISO containers. So the solution, this is a schematic of the solution, is that we've acquired 9 solid oxide fuel cells. These are 1.5 kilowatt fuel cells, electrical. They are single phase domestic use fuel cells at the moment, but they're the only commercially available solid oxide fuel cells on the market in Europe. so they can run on biogas as well. So we put the 9 fuel cells in a container which sits on top of the data center container, which is below. So these are 2 stacked ISO containers. We need to supply air to the fuel cells, and the air will come from outside. So we will heat up the air with the liquid immersed solution in the bottom container. So this is 22 kilowatts of IT, which is immersed in a synthetic hydrocarbon, which is a dielectric. So it collects all the heat, it circulates the hydrocarbon around the basin, and the heat is collected, and then we will preheat the air to the fuel cells. The fuel cells will then upgrade the heat, the return through a heat exchanger, the return line from the district heating network, which is in the adjacent building. And then this will be upgraded by the 9 fuel cells to be rejected back into the district heating system. So the fuel cells will need water, so we need to supply them with water. They've got water purification components inside them because they need very demineralized water, and we'll also provide the biogas to them. So we will have a battery solution, so a UPS, which will be in line with the power lines from the fuel cells. And since they are single phase, we are grouping them together, 3 fuel cells per phase of the power. And the batteries will hopefully either provide us when the fuel cells don't respond so quickly to the changes in IT, in power demand from the IT. So the batteries will be used as a buffer, either to absorb some of the excess energy or to provide energy. And if we can't do it that way, we are still connected to the electrical grid, which will supply power to the whole system, the whole demo site. And these are 2 20-foot ISO containers that are stacked on top of each other. The bottom one is a very, very secure container. It's impenetrable and weighs 25 tons with the solution inside, and the container on the top weighs about 9 to 10 tons with the fuel cells inside. So this just re-emphasizes the fact that grouping the single-phase fuel cells together, we would need to group them in groups, put them in groups of 3. We're still testing at the moment the thermal envelopes of the fuel cells to see how we group them together in terms of their heat provision. We could put them all in series, which has problems, or we could put them all in parallel, or we can put them in a combination, and that is still yet to be decided. But the power lines are clear, power provision. We will be monitoring power from the 2.
Sorry, John, 2 more minutes, please.
Okay, yeah, I'll go to the next slide. This is, thank you, yeah. So in terms of the last year's temperature, what was the temperature of the district heating network? It's a 3rd generation network. So we can probably reach 95 centigrade, and 95 centigrade means that we could reject the district heating system, district heating network at about 90 degrees, which will cover 80% of the year. The other 13% we will not be able to match the temperature. So we would let the systems reject the heat through the chimney stack that is involved with the fuel cells. So just quickly, I realize that I do have a habit of speaking too much. So some lessons learned so far is we will operate the data center between 10 and 60% utilization, which is common for a lot of data centers. So that will means that we have a sufficient power from the fuel cells to operate, but we do not think that we will be able to match the district heating supply temperature all year round. So that's the test that we're going to operate for 1 year to see whether we can. Of course, this demonstrator would run much better on a 4th generation district heating network because the challenges of access to gas maybe in some parts of Europe and lower temperature networks would make that easier. The solid oxide fuel cells do not have enough power density for data center applications. So that is something that the company that has provided us the fuel cells will improve their power density. And of course, the other aspect is the fact that this can run on natural gas, but if we can run it on biogas, then the opportunities for using renewable sources of energy improve, or mixing hydrogen into the mix that comes from storage of renewable energy. That would be an advantage to reduce our carbon intensity. My phone number is here and my email address is here if anybody has any questions, just in case there is not time for questions at the end. Thanks,
Yeah,
Maria.
well, there's no time. There is only one question. I think that you have already mentioned it, but Maria is asking about the operating temperatures from liquid cooling, district heating return, the hot water temperature supply to district heating. Can you remind
Yeah, so we can get
the
we should be able to get 60 degrees out of the hot water from the immersion system. So that will be able to preheat the air to the fuel cells. The fuel cells we anticipate should be able to get up to 95 degrees centigrade. The district heating operates between 72 in the summer for just hot water and 115 degrees centigrade in the depths of winter when it's lower than -20 outside.
Okay. Thank you very much, John. Then let's move quickly to another different project. We have closed the WEDISTRICT project, and now Federica Foglini is going to present the REWARDHEAT project. Ciao, Federica. Let's see. You're mute. Your microphone is off. Let me. Okay. Let me. We cannot hear you. It seems that your microphone is off. At least the icon of your microphone is off. No, we still don't hear you. Well, maybe we can go. We can continue with the next presentation and see if it's possible to record you. Okay. Yes, when you are try the microphone and at least to test it, and then we will be able to hear you hopefully soon. Okay, so then Antonio Garrido from Tecnalia is here, who is going to present the related project. So hi, Antonio.
Hi, can you hear me now?
Perfectly. You have to share your screen. Yeah.
Yes. I start sharing it. It seems that I start sharing it. Can you see my screen? Because it says I'm sharing it.
Yes.
Okay.
Just put it in full screen mode, presentation mode. Okay. The problem is that we can see the smallest one, so we don't see the full screen. But well, if the letter is not very okay, now we don't see anything.
So that would be better, I think. Just let me know if you're seeing everything. Can you see the big one?
No. Okay. Okay. Perfect.
So, yes, my name is Antonio Garrido Marijuan. I work for Tecnalia, which belongs to the Basque Research and Technology Alliance. I'm going to present the related project, mainly the lessons learned from this project. Related has been running for 3 years, so it's in the there are 4 demos. 3 of them are already working, and 1 of them is on the commissioning phase. What I'm going to talk about today is the demo of Tartu. In Estonia, this demo it's a part of a bigger district heating. It's a subsection of this district heating, which is operating at conventional temperatures. In the project related, we dropped this temperature of supply 10 degrees and start analyzing what was happening. So 10, 15 degrees was the reduction after the installation of a mixing chamber. Since we don't have too much time, I will go quickly through the characteristics. But the important thing of this subsection of the district district heating that we're using as demo is that there are over 50 consumers connected. So this is the substations feeding into the
Okay, sorry, I think that we have lost Antonio. It's only my problem. Can anyone write in the chat?
No, we lost him as well, Mavi. I think
we lost Antonio, right?
Yeah,
seems like
okay.
a network problem his end. Yeah.
Yeah, I think it's down. Okay. Well, these are things that are happening in real life. So, okay. So maybe we need to change to another presentation, and then if Antonio comes back, I hope that he will come back, can continue. But in order to not stop the workshop, I would ask Alexander, I don't know if it's possible that you present.
Yeah, sure.
Okay.
No
Hi,
problem.
Alexander. So you can share your screen. You're going to present the future district house from Matchup project. Thank you very much for being here. We can see your screen perfectly. Okay, thank you.
Okay, thank you for the invitation. And first of all, I want to introduce our Matchup project. This is a Horizon 2020 project. I will tell you, give you some facts about this. And my name is Alexander Heidan. I work in the business development department of Sachsen-Energie. You see it here. This is an energy company in the eastern part of Germany. And we came up with the organizers to have a little bit another focus of this presentation. And I want to share some information about our Matchup project, the District Future House, which you see here on the photo. But let me start with introducing the Matchup project from who didn't know this. We are for 3 lighthouse cities, Dresden, Valencia, Antalya, and have some follower cities in all over Europe. We are 28 partners in total, and the Dresden team combines the municipality of Dresden, the Technical University, Research Institute Fraunhofer, housing companies like Vonovia, transport company. So this is our consortium, and we are coming to the end quite near with this project. So that's why I can give you some information what came out of this. I told you that Sachsen-Energie is one energy company here in Dresden, the city where I live, about 500,000 inhabitants we have. And that's why most of our actions in the Matchup projects are dealing with energy, also ICT and mobility, but the focus is on energy. Last year, my colleague presented here some insights about what we are doing in the district heating sector within the Matchup project. You see here on these photos, there was an expansion of the storage vessels for the district heating in our innovation power plant. And we carried out a quite advanced measuring system there and checked for several weeks the operation conditions under these new circumstances. At the downside figure, you see something about our so-called low X program. This is something about reducing the inlet temperatures of the entire district heating system here in Dresden. which is one of the oldest and biggest in Germany. And we do all these actions within MatchUp just to facilitate the integration, future integration of renewable energies into our district heating system. This is the infrastructure side and the generation side of the district heating. But the title of my presentation today is the District Future House. And I want to give you some insights about this. First of all, why is this a smart building for us? I mean, you see, this is a quite nice architecture from our perspective, and it's a lighthouse project of the housing company. And we have there a high energy standard, and it is equipped with some communication infrastructure. So you see, it's a new built block in our lighthouse district Johannstadt. And you see that this has a connection to the water, to the district heating, to the electricity, and to the telecommunication network as well. This is nothing smart, this is normal, I think. As an energy company, we also applied a photovoltaic system and electric storage with this building. But to make this smart or smarter, we need some ICT infrastructure, and this combines all the commodities which are inside this building and also are connected to the flats. That means for us, we can provide services based on the submetering systems we installed there for the housing companies, for the tenants, and as well for us as an energy provider. And I would want to show you some information about this. The heart of this implementation is a building manager. And as I told you, we gather the information from all the commodity meters, also from the weather, from the outside weather conditions at this point, and the district heat transfer station is implemented as well. So what do we do with this? First of all, we make a billing of the cost of the energy costs. And then we derive the energy consumption and the weather data and share this with the housing managers. Also malfunctions are derived there. And we come up with this building from the demand side. And this system helps us to optimize our heat supply in this building and to reduce also the demand of heat. So, here you can see another gadget we installed inside the flats. So this elder man here is using his flat manager, his apartment manager, where he can see the energy consumption of all the commodities, also water, and has historical benchmarks. He sees the solar power generation from the roof, the room temperatures he can choose, each one, the weather conditions, and also some information of the housing industry. So he's able to control room-wise the temperatures, heat curves, the lights, the blinds, and the smoke alarm. What we implemented here in this house is also a so-called tenant electricity model. That means, as I told you, we have solar photovoltaic system on the rooftop and the storage system. And in Germany, we have the energy transition, and the regular way for the tenants is they pay for the energy transition, but they don't receive the energy, and so they can't participate that well. And with our tenant electricity model, it makes possible to use the energy produced on the rooftops for the tenants. So this is quite complicated in Germany. So as Sachsen-Energie, we have our own model to make this more easy and accessible. But this wasn't smart enough for us, so we built this a little bit up, and we called it the smart tenant. The tenant electricity model becomes smart. That means that we introduced the first time here in Dresden flexible tariffs. That means we gave to the tenants a visualization on their apartment manager. You see this on the yellow points here. These are time slots when energy is even cheaper for them if there is enough generation on the rooftop. This was one step, and in another step, we are trying to implement even more information about demand and production of energy. So at the end, the tenant profits of lower energy costs. So, okay. I mean, before starting with this project, we made a lot of simulations about the electricity demand and production, about the thermal demand. But if we are talking about future business models and services for the housing industry, for tenants, we have to test this in the real life. And that's what we did in the Future House, and what was from our perspective quite good. So we can give you some information about what we generated here in this house. This lady also is working with the apartment manager. He's also a tenant there. And I mean, we carried out also a survey on the tenants, what they are thinking about their future house and the opportunities they get now. Resulting that they quite appreciated the flexible and green tariffs, and they used their apartment managers nearly every day. There's also an app you can use as well. And for us, a quite interesting information was for our product management that 2/3 of the tenants, they change their energetical behavior by using the time slots where the energy is cheaper. So this was for the tenants. You see, we also monitored the sustainability. So we in every category we have a better sustainability compared to a regular building. But we are still working on elaborating the results, monitoring the results, especially from the heat sector. And for us, for Sachsen-Energie, it's quite important to get new business models, and we implemented the green and flexible tariffs. What is quite ambitious if you are thinking about the billing process, which is very complicated in such models. And so at the end, we got some new models, some services we can provide to the housing industry, to the tenants. So, I mean, this is at the end, it's a win-win situation. And we are at the moment disseminating this and multiplying this with other housing companies here in Dresden. So, okay, so that's all from my side, and hope you got some new information about this presentation, and I'm ready for your question.
Thank you, Alexander. There is a question, please, Alexander. Who owns the PV panels? Who's the owner?
Yeah, the PV panels owns the housing company as well as the storage system. But you can organize this model whether you like. Also, the energy company can own this, or if the housing company is okay with this, also the tenants can build up a cooperative.
Mm-hmm. And there is another question, Alexander. Have you seen people's behavior change as a result of them seeing energy information and price reductions?
Yes, we could see this. And that's quite the interesting thing. I mean, you can model everything and simulate everything, but this is real life. And we saw that there is a change of the demand, of the electric demand, using this reduced time slots for energy. We can see this, yes.
Mm-hmm. Okay, perfect. I don't know if there is another new question. If not, I think that we can try to talk to Federica.
Hello, can you hear me?
She's here. Yes. Thank you very much, Alexander, for your presentation. Thank you. Okay. Then Alexander stops sharing. Perfect. Federica, we can see you. We can hear you, which is really important. And you can share your presentation.
Yes, just a second. I will, from here, I will go. Okay, I think you can see my presentation, not in full screen mode. Now I will.
Okay, we see.
Is it okay?
Perfect. Yeah, that's
great.
Perfect.
Thank you. We made it. Thank you very much for this workshop and for the previous presentations, which were very, very interesting and detailed. I will present today the REWARDHEAT project. The REWARDHEAT project is a 4-year project. We started 2 years ago, so we are currently at month 24, and today and tomorrow the GA of 24 is being held simultaneously to this workshop. So we start with describing a bit of the background of this project. We know that 72% of the European population lives in cities and towns so far, and they generate a huge amount of, they consume a huge amount of energy. The characteristic of cities is that they are, for historic reasons, built around lakes, rivers, and seashores. And these sources are actually producing a low temperature renewable energy, are putting available this low temperature renewable energy. Also, not to mention the solar source. So the project wants to take advantage of this low temperature solar and geothermal energy. In particular, REWARDHEAT focuses on district heating and cooling networks and their capacity to recover this waste heat available from these city sources at low temperature, which means lower than 40 degrees. In fact, many of the district heating and cooling temperatures so far, networks so far, especially, of course, the heating ones, are very high temperatures for the conventional networks. And the project wants to focus on supplying temperatures lower than 60 degrees, but down to 10 to 20 degrees. Also, one vision of this project is to focus on the exploitation of the energy sources available within the urban context, so to allow the maximization of this potential. The project is actually coordinated by EURAC, and we are a 30 partners consortiums, where RINA plays the role of demonstrators, of leading the work package of demonstration activities. The specific objectives of this project are many and revolve also around the development of new technologies and solutions for the district heating and cooling networks. In particular, the first specific objective is to integrate multiple urban renewables and waste energy sources into the network. For these reasons, we are exploring different district heating and cooling configurations of the networks, trying to merge the different sources. And we have some tasks on the project, in particular, for instance, the planning schemes database, the pre-design tool, information material for publication in wiki tools, guidebooks for planners, and serious gaming, which is also a proper game which we are developing as part of the projects. Of course, these tasks are all involved the new schematics and designs of networks, but from different perspectives. Also, a specific object of the project is to develop innovative technologies for flexible use of heat in district heating and cooling networks. In particular, here in this project, we want to develop the substations where we follow two different approaches. One is the prefabrication one for building solutions, and the other one is to standardize the large-scale ones for heating plants and energy centers in general. Here we have two types of solutions developed by the project. One is the small size, up to 50 kilowatts, prefabricated substation, and the other one is a large-scale industrialized energy center. The small size heat pump is developed by Danfoss, while the large-scale industrialized energy center by Oxner as a partner in the consortium. Also, the project develops new piping for the district heating and cooling networks for low temperature networks. In particular, this is developed by Thermaflex, and we have prefabricated and pre-insulated pipes. Another technology from the project is the thermal storages. We are proposing in several demo sites different thermal storages, in particular the local ones, intraday storages at customer substations directly, the central intraday storages to balance the network and store the energy, and the central seasonal storage, so borehole storages which have capacity for the whole season. There is also another work package and another aspect of the project which focuses on the demonstrating digitalization of solutions that allows to optimize the management of the district heating and cooling network. This part involves many different tasks, and for instance, the smart metering communication in real time, but also the data mining platform, which is currently ongoing in several demo sites, and with permits to manage the communication with the smart meters on these very large district heating networks, and also the fault detection systems and predictive maintenance. Another specific objective is the development of business models. In fact, for this new type of district heating and cooling networks, lowering the supply temperatures and integrating new technologies also require to develop specific business models and financial schemes for raising investment in this, not only for public but also private investments. So there are specific tasks that are focused on the development of business models and to pass from the heat as a commodity considerations so far to the heat as a service model. There is also a financial support approach that is elaborated based on reliable and transparent information, and we are having many different workshops with local stakeholders actually now in these months. And now here we move into the part where RINA is mostly involved. So it's Work Package 6, the rewarded demo cases. Within this project, we have many demo cases. It's 7. We name them 7, but actually both in Milan as well as in Sweden, we have 2 demo sites, and they are very large because they include both district heating and cooling. So they are entire districts, city districts, if not larger. In particular, we can see that we have one demo site in Milan, which is led by HUA. And here we are developing new built neutral temperature networks in two sides of the city. Then we have Szczecin in Poland, where we are also building a new low temperature network. We have Albertslund in Denmark, which is a retrofitted network to move it to pass from a conventional temperature to a low temperature. The Swedish Helsingborg and Mölndal, where we are building new low temperature networks. Topusko, which is in a heat cascading in a low temperature, also a conversion from a standard temperature network to a low temperature network, exploiting groundwater wells. Toulon in France is an upscaled neutral temperature network, which already exists. And the Erlen in Netherlands has the goal of installing an intraday storage in neutral network temperature. This table has been specifically prepared to show where we stand in each of the demo sites. As you can understand, these activities, also many of the presenters before explained, requires often a different budget than expected, different involvements, a lot of permits. There is really a lot of going on for each of these demo sites. So the project was very ambitious. It's still very ambitious, of aiming at having all these 8 sites installed within the time frame of month 18 to month 30, but actually we are seeing that some countries have been able to perform installation much earlier than others. And this is due to the many constraints that the presenters before explained. In particular, one of our complicated situations, we can say, is the Milan one. In Italy, the permitting is very long and complex, and for these two newly built networks, one of which recover heats from transformers, for instance, it's very complicated. So we are still working very closely with HUA and DEVRAC for moving forward. But as you see here, the timing is a bit delayed compared to the expected, as well as Erlen, the installation of the large intraday storage, which originally was supposed to be 500 cubic meters, if I'm not wrong, was huge and required a lot of work. So now we are still in the process of defining if this is applicable for that demo site, or if we need to move to a smaller size, more easily to manage and also to invest on. Topusco, the heat cascading in low temperature network, it's also an interesting case because it uses groundwater, hot temperature groundwater available at around 80 degrees, if I'm not wrong, and we need to reintegrate into the spa. It's into an health center, which wants to take advantage of it. So we have we are facilitating because there is a private investor which is already willing to integrate this heat source. At the same time, there is a need for the end users, for the local users, to perform this work only after the winter season. So for now, for instance, we think that actually this time plan is even too ambitious, and we need to start the work and to perform the final commissioning of the system only after the winter season is over. And then we have other demo sites where the problem is not, there is no problem related to permitting, let's say, but also they have a different situations. For instance, Toulon in France, they haven't performed physical interventions, but just, let's say, control aspects interventions and an EPC study, and therefore these activities have been able to progress steadily. Szczecin is a new demo site. It's actually a replacement of Hamburg. In this case, it recently joined the consortium, and therefore it's still in a good track. But of course, we don't expect it to have all the activities right now already completed. While projects that have been moved pretty good is, as I said, Helsingborg and Mondal, which built new buildings and from scratch, and I will show you pictures afterwards, and also Albertslund, which I will go in more detail in the next slides. As you can see here, in fact, Albertslund had a scope which was to reduce the temperature in the Porsanger district of the city of Albertslund. And they wanted to move from 85 degrees to a lower temperature of 60 degrees by supplying from a mix of different sources. This, of course, requires many different actions and challenges. The first one of which was to reduce the district heating supply temperatures by means of a shunt valve. And what you can see here, in fact, is the process of installation of the shunt valve, which has been really put in place. There are other steps to follow here. Where the work is not completed, that you could see also from the previous slide. So we need also to install later a prefabricated skid for critical customers, which can be covered by the very low temperature that this shunt valve will deliver. We need to exploit local waste heat also from 2 supermarkets to increase the penetration of wind electricity by means of intraday thermal storage and heat pumps, but also to integrate the dynamic and control software to optimize the full operation of the district area and develop innovative business models for the final customer. We have some progress in this sense. Let's say that the point 1, so the next action, we have seen that we don't need so far to install further booster heat pumps for raising the temperature in the final customers. So that's a good news. It means that the shunt valve performs as expected. And also concerning the integration of waste heat from supermarkets, this is a very interesting case study for the project. We are performing a feasibility study which should be finalized by October. Still, we do not have any news. And this one here, that you can see, are some pictures for the newly built Helsingborg and Modal buildings in Sweden. So here we built from scratch two new buildings with borehole thermal storage. In particular, in Helsingborg is a low temperature network that explores the borehole seasonal thermal storage system with a centralized heat pump and the reload of heat from the industries nearby, while Mondal is a novel low-temperature sub-network, so the network was already existing in great part, similarly to Helsingborg as a seasonal thermal storage, and uses a centralized heat pump, but also local heat pumps for hot water. And that's it, I think, for a bit of insights on our demo sites. These two were the most advanced ones, so I thought it would be interesting to show a bit of details of this. This is, of course, a teamwork done with my colleagues together in this Work Packet 6. I hope you enjoyed, and I'm here for any questions.
Thank you very much, Federica. Very interesting. Also, your experiences with your demo sites. It seems that we are facing similar barriers. What do you think is the most difficult one that is delaying your projects, or what do you think? Because in our case, I think it's the permissions, but I don't know what you think, or what is your experience?
In this project, we are seeing being the work package leader and not the coordinator. Actually, we're having very deep technical conversation monthly with each of the demo sites, but finally we are also, there are some aspects, for instance, the financial ones, as you know, that we are not discussing directly with the demo site, that goes to the coordinator, let's say. But for what we can see technically, in Italy is the permitting, the most difficult part. So this part is really delaying, while the other critical situation could be in Ireland, in Netherlands, the intraday storage solution, which is a very large, very complex one, where we are not, it's not easy to find still a business model and a suitable business models also for justifying the investment, let's say.
But because of the maturity of the technology, or because of the business, or both, because the business model is, you have to create a new business model for that?
I would say, yes, that is because we need to create a new business model for that. We need to be able to justify that this new seasonal, very large seasonal storage would be able to bring the real benefits to the system compared to now. Probably is also because the current system is very complex, is very, the district in Ireland is very complicated, so it's even hard to put the hands on it. That's our experience, at least for what we've seen.
Thank you for sharing. Okay, it's supposed that Antonio is here, but I cannot see you in the panels. So if you are here, Antonio, but I don't see you, so I don't think that you can present. Okay, yes, you are here. Okay.
I don't know what happened. You can hear me.
Yes, perfectly.
I don't know what happened.
Do you have 5 minutes, please?
Okay.
Sorry, because we are a little bit delayed.
No problem. I don't know. I think you heard this. I don't know. I will just go very quickly.
Yes, you was talking about Tartu.
Yes, I was talking about Tartu. This is one demo of the related project, which is looking for ways to go into 4th-generation district heating. This is operating at lower temperatures than conventional district heating are operating today. There are a mixing chamber was installed in Tartu, so we could reduce the temperature of supply in a subsection of this larger district heating. And this will be a scheme of the different substations that are connected to this sub-network. We were collecting data from 5 different points at the supply, at the main primary site of the district heating. The substation will be the district heating network. And at the secondary site of these 2 heat exchangers will be the domestic hot water consumption and the space heating consumption. As I said, we are collecting data for 24 months of monitoring. So that will be more than 2 million data entries. And this is normal data. I mean, this is nothing big. So traditionally, the inspection of the data is a resource-intensive task because it's done in a very conventional way. No, nothing fancy, nothing automatic. So only the most important substations are carefully analyzed. Tecnalia, as partner of the related project, make an automatic inspection of the data in order to extract conclusions. So what is happening at the different sites of the district heating. In this slide, you can see 3 graphs representing 3 substations, the primary side of 3 substations. This graph seems to be very easy graph, very understandable graph, but it comes from 2 years of monitoring from the district heating. So this is a large set of data summarized in one graph. The first graph on the left, it's a substation operating as expected. So the cooling at the substation in the supply side, in the primary side, would be more than 20 degrees. This was expected, and this was planned by the district heating operator. But in the rest of the graphs, on the middle and in the right side, there are problems, and we found these problems thanks to this automatic inspection of the data. In this case, the cooling is not as expected, as planned by the district heating operator, because it's lower than 20 degrees. And in this case, on the milder part of the heating curve, the response curve was not as expected. Regarding the secondary side temperature on the space heating heat exchanger, we also inspect these 2 years of data entries. These are the outcomes. So on the left is an example of a normal operating district heating substation, and on the right you can see a malfunctioning substation where the response curve is not so good one, and this is because the flows were not set as planned. They were operating in an unexpected way. Regarding the domestic hot water inspection of temperatures, for the summer period, we graph the domestic hot water temperature supply to the customers for every hour of the day. And we found that some substations were not supplying the healthy temperature or requirements of health to avoid Legionella as expected, and these were informed to the district heater operator. As lessons learned from this task of the related project is that data monitoring is an essential tool for district heating optimization. We know that machine learning techniques, low-cost monitoring, and so on is bringing data-driven science to the district heating operators, and this is very important because until now the analysis of the data was a time-consuming task, but with an automatic way, it's easy to improve the district heating operator, identifying issues in real time. Also, we found that the inspection of data, of large sets of data with a normal laptop, so the laptop that I will be using for daily task, it's very easy. We were able to analyze data from 54 substations in less than 10 minutes. So this is really low cost for the computational cost. It's for us, it was a surprise that the large district heating operators often lack this kind of service, so they are not inspecting the data with the latest techniques. Some of them, of course, one of them will be doing this, but there is a need for district heating operators to move to the automatic inspection of data, because that will help them to have a proactive approach to further optimize the district heating operation, because as today is not exploited. So I hope I was within the 5 minutes you gave me, and thank you very much for attending. I'm open for any question.
Thank you, Antonio. I don't know if there is any question. Yes, Antonio, what are the extremes of temperature of the supply of district heating?
The extremes, so before the, so I think you mentioned this part. So before it was 90 degrees, and after the implementation of the mixing chamber, we are operating at 80 degrees at the worst conditions of outdoor temperature.
Mm-hmm. Antonio, have you implemented this kind of data analytics in other district heating projects?
Yes, so we have 4 demos in the related project. 3 of them are already working, and we are doing the same for Belgrade, which is a large, also a large district heating. We are operating in a sub network again, and yes, also they have reduced 10 degrees or to 15 degrees the supply temperature. In this case, answering to John, maybe he has also this question. It's higher than in the Tartu one. I think they were operating at 100, and now they are operating at 85. Something. I think that's the values, but that will be very close to the ones I said. And also for another network in Denmark, we are doing this kind of analysis, automatic analysis.
Okay, great. Okay, thank you. I don't know if the
of course.
Okay, thank you very much, Antonio.
Thank you very much.
And let's hear your presentation complete. Okay, so then there is the last presentation that will be done by Frederick from Ramble. This presentation also is part of a study done in WEDISTRICT project and gathers interesting suggestions for the district heating and cooling world. Then, Frederick, you can turn on the camera and share your screen.
You cannot see me now because my camera should be on.
No, but I think it's more important to hear you, and we can hear you. Okay, we can see you as well. Okay. And if you can share your screen. Do you have maybe 8 minutes presentation? If you can do it.
I will try. I will try to keep it short. I have cut away something along the way to meet the time. Can you see my screen?
We can see your screen. Yeah. Just put it in full screen. It's a bit slow, but
okay.
Okay, we can see your presentation. Great.
Perfect. Yeah, my name is Frederik. I come from the Danish consultancy Ramble, and we're part of the Redistrict project. And this is a presentation on a more high level. We have been looking at the current stock of district heating and cooling in Europe. We have looked at future development trends and district energy markets in Europe, and also identified some inefficiencies, barriers, and also suggested some improvements. Yeah, so what we did was we looked at all the European countries to see what share was satisfied by district heating in the total heat demand. And we divided the countries into 3 groups: a small share group, a medium share, and a large share. And we found some general aspects from each group. So in the first group, small share, which has less than 10% covered by district heating, we saw there was a lack of culture and no master plan, and also, as mentioned before today, that the regulatory framework was not really existing or lacking incentive to do district energy. We also found a high use of individual heating and fossil fuels, and also we noticed that it was associated to warmer climates. For medium share countries with 10 to 50% of district heating, we saw fossil fuels or biofuels as the main fuel, and also a lot of individual boilers. And heat price and CO2 emissions was still favoring individual solutions. There was no taxes or anything that should make it more feasible to do district energy. Some of the countries had district energy systems, and we saw that they were in need of refurbishment. And looking at the large share group, here there's an increased focus on biofuels and electrification to large heat pumps, but also on improving the existing production and introducing more renewable energy. Yeah, as mentioned, we saw there was a lack of cultural and historical background in some of the countries with little or less share of district energy. And this makes it difficult for investors to have stable conditions for long-term investments. So if you're not allowing to have long-term investments, it is a problem, because district energy systems is an infrastructure that costs a lot of money, and you need to have a long time to pay for it. Also, we saw that some countries of national building codes favored individual solutions over district energy solutions, because the energy efficiency directives from EU was not implemented at the same degree. So this can lead to a sub-optimization and not necessarily the most cost-effective solution for communities. On the right, I have taken a table showing the different generations of district energy, district heating. And as we have talked about today a lot, the temperatures should be going down to increase efficiency and economy. We saw countries at very different stages, but very few was on the 4th generation district heating yet. Some were moving towards it. And what's important to look at here is the combination with district cooling, which is very interesting and relevant to look at in the future. Yeah, so we have a list of suggested improvements. It is difficult because there's a huge variety of the systems and climate zones in the European countries. So it is a different starting point in each country. But generally, creating a stable methodology and guideline to carry out cost-benefit analysis of heat supply options is necessary. Also, creation of long-term financing schemes in line with other infrastructure projects will benefit the integration of district energy systems. Have access to laying pipes in public and also, if necessary, private land will also benefit the expansion of district energy. And ensure fair competition between district heating and cooling, and also building living solutions. So implementing the EU directive in a similar way to the same degree in each country is also relevant. And then retrofit the existing district heating and cooling systems to provide a higher technical and institutional performance. This could be combining heating and cooling, as I mentioned before, installing pressure and temperature control of all end user substations. So many of the things where we have talked about today. Yeah, the stage of district heating systems is also influenced on the development of district cooling. So if you do not have a well-developed district heating system, district cooling, combined district cooling and heating could be more difficult to implement. However, it is possible to do district cooling without district heating. It's necessary to create regulations with the purpose of protecting the consumer, including price and/or profit structures, and transparent for your utilities. And this should be done in close cooperation with industry. Also, we see when we're planning cities, energy planning is very important and should be seen as a natural part of urban planning and of infrastructures. In Ramble, we do a lot of energy planning, and we divide cities and regions into zones to find out what zone is best suited for gas, could be biogas in the future, district heating, or individual heat supply from heat pumps. And this makes sure that we do not compete within the same areas of parallel infrastructures, and we have a clear boundary of where to expand this system, and this also makes it easier to expand the systems of district heating in a more focused area instead of two large areas. Yeah, district heating has a significant market share in countries with has a public utility, and we can see this also when looking at the long-term investment schemes. That if you have a public utility, it is more it is easier to expand the district heating systems. Yeah, and attaining reliable and long-term energy solutions call for the right structural balance between private sector knowledge and public sector framework, which enables district heating infrastructure to long-term by having a relatively clear view of the future market change and low risks. So this was some of the improvements we found in the analysis of district heating systems, and I hope that was about it. Thank you for listening, and also please see our newest article in the Hot Cool paper. I provided a link here on this topic. You're of course welcome to contact me if you have any questions.
Thank you, Frederick. Thank you. So now we are out of time, but yes, I wanted to inform the audience that the information that has presented Frederick is part of a public document, which is in our website. So you are free to read it because it's really interesting. And I wanted to close, before closing the workshop, I would like to just to steal 1 more minute with the new questionnaire, interactive questionnaire. So please, just as a conclusion of this workshop, which are the improvements that do you think that are needed for facilitating or improving this kind of projects implementation? So you have to go again to menti.com and use a new code, okay? The code is 8693253, and just give us your thoughts. Well, Frederick has already explained a lot of suggestions for improving, but just in case you would like to also to add a new one, you are free. Or if you have to say something, feedback or thank you or wherever, we will be able to see you. Let's see if you can do it. I will wait 1 more minute, I promise, and I will close the workshop. I don't see anyone. Nobody wants to write. Nobody knows what are the improvements needed, what we can do. I think that we have, Frederick has shared all the ideas, but you can repeat, don't worry. I hope that it works. Maybe there's a problem. I don't know if you could. Okay, menti.com doesn't work. It seems that doesn't work. Okay, yes, people. Political goes with subsidiaries and municipal plans. Yes, for sure. Thank you. Anonymous. Okay. So, well, this is meeting procedures. Yes, please. So I don't know if there is any public body here that can, well, speed up this kind of procedures, because it's true that, well, it's well, a very big barrier for us. Public awareness, right? Better insulation of buildings. Yeah, that is part of the or the next generation. Yeah. Well, I have to say that this questionnaire will be well, operative during today, so you can keep writing things if you want and to share with us. It's time to close the workshop, so I hope that you have enjoyed and you have learned a little bit. And please, all the speakers, turn on your camera just to say goodbye. And I hope to thank you very much for your participation and your interesting, presentations, and also for sharing with us your knowledge. And I hope to see you soon. And thank you also to the audience for participating in the workshop. And thank you to Sustainable Places for bringing us the opportunity for organizing this workshop. So,
Yeah, thank you very much.
Would like to say anything else?
Thank you, Mavi. Yes.
Thank you.
Thank you.
Thank you very much,
Thank
Maria.
you all.
Thank you.
Okay.
Thank you
Thank
all.
you. Have a nice day. See
Bye
you.
now. Bye bye.
Bye bye.
Bye.
Thank you.
Bye.